session of the meeting. This proves to be a very exciting set of talks that wrap up the 3 days, 2.5 days. So I'm really excited to hear the presenters. Just as a small postscript to Alistair's talk yesterday, I can't resist him not saying this actually, that what you have to understand that Isaac Newton was a very clever man. We all know that. And his great rival, Hooke, was a man of decadence. But what you have to understand is that Hooke was from Oxford. So as an Oxford person, it gives
What
me
are the
great
details on the decadence?
it gives me great pleasure to introduce our next speaker, who needs no great introduction to this audience. But Jim, welcome, and we're going to hear about the physiome and multi-scale modeling towards human health, multicellular and multi-organ.
I can't pretend to do everything, but I have, I think, some hints as to at least what I believe in, and they're probably. I'm talking to a choir here, of course, that everybody's beliefs in this room. You're on a mission to do multi-scale modeling, quantitative, analytic, and so I don't think I have anything new to say. And so at this point, I should sit down, but given the opportunity, I won't. So everybody knows that physiology is based on anatomy, and that we can't do any physiology without anatomy. And so my plea and the first part of my talk will be centered on the idea of keeping in mind the anatomy, because it influences the physiology in some striking ways, not only in overall, let's say, muscle mechanics, but in molecular mechanics and molecular behavior. Dennis introduced us to the idea of middle out. Practical, go from where you know something. There are other ways of attacking the idea of unraveling the importance of the genome and putting it in the context of human physiology. And I find those problematic, and I would argue that the strategy is not well founded at this point. So I'm going to make some rude comments about that kind of thing at the end of my talk. And the other is coming from the phenotype to the physiology, which seems like a natural thing, is also not so easy. This book you know about, but I wanted to emphasize it. It's just a lovely book that Dennis has put together with this set of ideas that you heard at the introductory talk, and it's just beautiful reading. He says it's just bedtime reading. It's much more than that. Enjoy it. Integrative analysis. We can do descriptive things, find the kinetics, and if we're looking at sets of biochemical reactions, you don't see much relationship to the anatomy there. But there is. We can take an explicative kind of viewpoint and look at the biophysics, the thermodynamics, the kinetics that come out of those things, constrained by them. We can look at cause and effect relationships. And we're trying, in order to get at those levels, we've inevitably taken a reductionist approach. Reductionist, some people think that's a kind of pejorative way of expressing what we do in biology, and we want to be integrationists. Realistic, anatomy-based, use the physics and the chemistry that we have treasured from our childhoods. Multiscalar. Now, here's a way of taking what's going on at the cellular or biophysical or biochemical levels and thinking in a causal way toward physiological phenotyping. Very difficult, because the whole underpinnings of such a scheme, going from the biophysics to the function of a body, is hugely complex and computationally out of sight. Modularity is a means for being reductive about certain components so you capture their behavior and don't represent the detail. We're all trying to do that in one way or another, and most of our models implicitly contain what would be called reductionist or elements. So we want to be integrative, multicellular, multi-organ, inevitably hierarchical, multi-modular, with the ideas that you can have modules of differing degrees of complexity depending on the purpose for which you like to use them. All of this is, of course, the physiome. That's what we're here for. So, physiome, quantitative description of the functional behavior of the physiological state of the individual of a species. Now, the second sentence is pretty questionable, but in a way, you'd like to be able to do that. And the question is it necessary to do that? Is that too big a project to think of seriously? Or are there some ways of doing it, coming from middle out, down toward the genome, up toward the phenotype? So this would be the idea that the modular elements that are the real reductionist things, the channels, the biochemical reactions, the signaling pathways, and so on, are then built together, sets of them into another module. This might be a reduced form of what's represented in the four things under its corners. And so on, and the top level model might be a multiply reduced form to represent the circulatory and respiratory systems and the responses to change in PCO2 governing the respiratory rate and so on. Now, underlying all of this is this idea of Goethe's static skepsis. This was used by Thomas Henry Huxley in advertising Darwin's ideas. Maintain your active doubt. And in this modest approach to persuading people that Darwin's theory of evolution was reasonable, he persuaded them also to think about it carefully. So, as part of our thinking, retain your active doubt. I translate this in one case to don't trust even a single molecule. It's not going to behave necessarily as you expect. It won't be influenced just by phosphorylation processes and glycosylation, et cetera, but also by its neighborhood, the actual physical location where it sits, what its competition is, what the pH is, of course, but it may not do what you expect. So I'm going to step aside here just to show you a single molecule behavior. This is a program written in JSIM, and all it is a single enzymatic reaction. The reaction is that the substrate binds with an enzyme with an on-rate constant K1 to form the complex, and then that's a unidirectional reaction to form product. The enzyme is generated by transcription at a constant rate and degraded when it is in the free state, but not when it is in the bound state. That's not a bad generality for enzymes, that their proteolysis is inhibited by the binding of substrate. The second part of this funny reaction is that the substrate concentration is given a mild sinusoidal form. So the reaction to form substrate is given by this sinusoidal thing, a small amplitude, and so the concentration of S is the driving function. The reaction on to form the on reaction and the off reaction. The enzyme substrate complex as a function of time is the on reaction minus the backward reaction and the forward reaction. And the free enzyme, of course, is what's left over, so that the free enzyme concentration is just given by the difference between the complex form and the total product is formed. Okay, so now what we see over here is the dynamic response of this system, the single enzyme. You look at it as a function of time, and so if I run a solution, oh, come on, I've lost my cursor. Lost my sound. Where'd the cursor go? Oh yeah, all right. So we'll go to runtime and hit the run button. This is set to run for 6,000 hours. And you see it reproduced this chaotic pattern. Well, I didn't use a millisecond time interval. So anyway, so this is an unstable situation that's sitting on an attractor. Well, it's analogous to many systems in our body which do not run with precise control, but rather a wandering control, which through baroreceptor control is an example of Meyer's waves recognized a century and a half ago, are slow blood pressure waves of a kind of ergodic nature, and they come out of the system as a whole. They're a chaotic response, and you remain on an attractor, which is then stable, easily governed, and you know where you are approximately. And so there are lots of systems like that. All right, so I'm going to escape from this, get rid of that, go back to now some other funny things happen with enzymes, and one is that an enzyme sequestered in a vesicle has a behavior that's dependent on the rate of entry of substrate into the vesicle. So if you calculate this reaction rate or fractional saturation of the enzyme in the particular case, and let the reaction rate be proportional to that, as in a normal Michaelis-Menten type reaction, then if you have a slow on rate, oh, my labels fell off. These are slow, these are fast on rates, and these are slow on rates. And what it does is it pushes the profile of fractional saturation versus substrate concentration to the right. It also steepens the curve, so that if you calculate the Hill coefficient at slow entry rates or slow on rates to an enzyme, you get these very high Hill coefficients that are an artifact. And the reason for me presenting this is, A, that's not what you usually expect out of an enzyme. B, it turns out that this is an important regulatory component for the utilization of adenosine on smooth muscle receptors in the heart. So we're going to come back to this idea. So the next part of the talk is on an example of looking at the mixture of anatomy with the physiology. And the setting for it is a set of studies that we've been doing over the years using PET studies for cellular hypoxia, S-adenosyl homocysteine concentration, using multiple indicator dilution studies for nucleoside transformation, adenosine, inosine, hypoxanthine, xanthine, uric acid, a reaction which occurs in endothelial cells and in cardiomyocytes, and using MR to look at phosphorylation events. Now I'm going to cover really only the indicator dilution studies. So in this set of reactions, if you block the adenosine kinase, this is a really fast cycle, very rapid reaction. This is also a rapid reaction. You'd think this might be a futile cycle, but it turns out to be a controller. If you block this reaction so you cannot form AMP, this reaction continues, delivering adenosine at an abnormally high level into the cell. That has some influences on blood flow. So here's coronary blood flow as a function of the dose of iodotuberosiden, the kinase blocker. And it looks like a standard Michaelis-Menten type of relationship, as if you have a single site binding to a receptor. So that's kind of the thing that you'd expect. So if you look at the adenosine, which is the agonist that's released from the cell into the interstitial fluid space as a function of iodotuberosiden concentration, you have this. So now you can then develop the relationship between venous adenosine and flow. So here's the setting for it in an anatomic sense. This is blocked. This continues. Adenosine is released, gets lost into the circulation, and you can measure its concentration in the outflow. But it's also taken up by endothelial cells. But if you've given iodotuberosiden to block this reaction, it's going to do the same blocking in the endothelial cells and in the smooth muscle cells as in the cardiomyocyte. So it's blocked in all of these places. And so it's available to affect the A2 receptor and relax the smooth muscle. But we tackle this firstly with the multiple indicator dilution technique, in which you inject a set of tracers into the inflow, in this case to an isolated ringer perfused heart. You can do it in blood perfused hearts, and you can do it in vivo, and we've done all of those. You calculate then the impulse response, the transport function, h of t. It's the flow times the concentration in the sequence of samples divided by the dose of the particular tracer injected. In this experiment, illustrated here, D and L-glucose are the substrates of interest. L-glucose does not enter cells since it can't get transported on the stereoselective transporter, and D-glucose then does. So you look at the intravascular indicator, the extracellular indicator, the L-glucose, and use those two as references for the metabolized substrate, transported and metabolized. Now you do the same thing with adenosine. So here are adenosine outflow curves in a rabbit in the upper panel and in a guinea pig. In the rabbit, this is actually, in this particular graph, it's inosine was the substrate used, which is the breakdown product of adenosine. And you see a small difference between the extracellular marker, which is arabinyl furanosyl hypoxanthine, has the same molecular weight as adenosine. And then the inosine, same molecular weight as adenosine minus an amino group. That's the guinea pig. So they're quite close, not very much uptake in the guinea pig, the rabbit. In the guinea pig, the transport is higher, and so the diffusible or permeating tracer has a lower outflow curve, and there's more has been taken up into the cell. So that's, out of that, you have to then do some modeling analysis in order to elicit parameters. So in this, now this is the case for adenosine and ARA-H, the extracellular reference, and albumin, ARA-H and adenosine have been injected together, and we're looking at then the product formation. The first step of deamination is inosine. The second step is hypoxanthine, and then xanthine is reacted by xanthine oxidase to form xanthine, and xanthine then is reacted to form uric acid. Well, this becomes interesting because the hypoxanthine is an exceedingly low concentration, and its product down 2 steps further, uric acid, appears in high concentration. So that means the hypoxanthine and the xanthine have been held onto the xanthine oxidase through 2 steps of reactions, not released so that they could escape from the cell. So here we have the rabbit versus the guinea pig again, with injections of adenosine and this series of products formed in both cases. Aha. So what's this stuff? Rabbit doesn't have any xanthine oxidase, but we've got a kind of noise level production of an oxidation product that's down by 10 to the minus 5. So there is a little oxidation that appears probably in the process of the sample sitting around before the HPLC separation. And so this part of it in the rabbit is seemingly an artifact. But in the guinea pig, which has xanthine oxidase, these are not very much higher, but measurable. So the model then uses a multi-capillary situation where one capillary is represented by flow through the vascular space marked by albumin, penetration of the clefts between endothelial cells, transport into the endothelial cells via transporter, the extracellular space, which is being marked by ara H here as well, and the albumin is restricted to this space, cannot get through the clefts. So we've got 2 inbuilt controls with every data set, and then the reactions are going on inside the endothelial cells and the cardiomyocytes. This particular type of experimentation gives you good information on endothelial cells, relatively poor information on cardiomyocytes. Here's some fitting of the curves themselves. Albumin, ara H, inosine producing hypoxanthine. So this was the injected tracer in this case, the inosine, and the inosine curve is this one, and the hypoxanthine product formation is this one. Now when you use adenosine as the injected tracer, then the products are inosine and hypoxanthine. Here's the inosine and the hypoxanthine. So via this analysis, in this case, we don't have it was a better experiment, and we didn't have the xanthine and the uric acid showing at all. So these can be then parameterize the experiment. Well, it looks like a complicated experiment. It's multipath. So to approximate the regional distributions of flows, we use a 7-path system to define the probability density function of the flows. It's multi-solute. We injected 3 and got 5 or 6 or 7. Modular. Each of the modules, the capillary tissue exchange unit, represents a different pathway with a different flow, but the same reactions and the same parameters for those reactions. It's multicellular in that you have both endothelial cells and cardiomyocytes. This model did not have the smooth muscle cells in it. Transport into the cell is via transporters, which are saturable, and the metabolism is intracellular. Geometry described by partial differential equations. Multipath. We use the constraints of the anatomy. A part of every experiment are the data that we observe, those concentration time curves, and the data on the anatomy. The capillary volumes are known within narrow constraints from steady-state tracer experiments, as is the extracellular space. So those are serious constraints not to be left out of the analysis. Reference solute 1, albumin. Reference solute 2, extracellular. So we sequentially optimize the data to fit, first of all, the albumin, the intravascular tracer, so the whole inflow to outflow through the heart is characterized by the albumin transport. And then secondly, with the extracellular solute, the ARA-H. Then the rest of it for the reactants species that enter the cell, they're all optimized simultaneously with a common set of parameters for all of the indicator dilution curves. Those depend then on the parameters that are used unchangedly from what was found for solutes 1 and 2. That includes the permeation between through the endothelial clefts. And finally, you get parameter confidence limits. So you can get some reasonably sensible data out of this kind of experiment. So the reaction sequence occurs, yes, as expected. The reactions are fast. We saw that the adenosine appears as a product of adenosine deamination within a fraction of a second, within the sample time. So the reactions are fast. For the adenosine, we have these reactions on xanthine oxidase, and it appears that the products, the substrates for the xanthine oxidase two steps of reactions are not really released once bound. We learned that rabbit has no xanthine oxidase. The tracer technique is limited. Doesn't give any information on the saturability of the process because we didn't measure anything but the tracer. So you know nothing about the actual binding site affinities. So that requires another set of experiments. So if you go after this, after the transport characteristics, you'd like to know the KD for the binding and these transport rates, and on the other side, the KD for the underbinding. These are traditionally put in terms of a transport max, like a Vmax for a biochemical reaction. So this would be a Michaelis-Menten representation of it, but you really need to provide this level of detail in order for it to make good sense biophysically. Here's a set of experiments then of adenosine at different concentrations in the background. So the experiment is to perfuse with an adenosine containing perfusate at 4 micromolar, 21, 50, 840, a whole set of concentrations, and then measure the transport rate. So the effective permeability surface area product put in this form are given by the data, and the estimated Km for the transporter affinity, or a KD, is about 112 micromolar. Ooh, that's startling, you might say. The background normal concentration of adenosine in the plasma is a few nanomolar, let's say of the order of 2 to 20. It's fairly variable, but it's now, you see, 4 orders of magnitudes less than this. So this is a transporter of low affinity relative to the substrate concentration, but a very high capacity. And this is going to impact how we look at the regulation of vasomotion. So what finding that transporter characteristic does is allows us to make some calculation of what the interstitial adenosine is. So we go back to that experiment in which we had used the iota tuberosidin to block this, and so that we get AMP converted to ADO, leaks out into the interstitial space, vasodilates. And now all we get of that, through then, now the parameterized model allows us to calculate what the interstitial concentration must have been when we could only measure the venous outflow. And it's not that much higher. It's just a factor of 3 to 4 higher in the interstitium than in the outflow, because all of those cells are losing the adenosine to the effluent, not just the cardiomyocytes. So in that, now let's do a different experiment, because the result is dramatically different from what we just looked at in producing coronary flow. This experiment is to infuse adenosine at varied concentration and look at its effect on the relaxation of the smooth muscle by adenosine binding to the A2 receptor. So the flux is now from the flow into the tissue, not the other way around. Here's the result. Startling. Coronary blood flow on the abscissa, the plasma concentration of adenosine at these different levels. So this is a whole host of experiments at different levels of adenosine and looking at the vasomotor response. If you block the A2 receptor with 8-phenyltheophylline, it's a competitive blocker, so you can overcome it if you give high enough adenosine concentrations. So it takes about in this particular, for this dosage of 8-phenyltheophylline, took about a 10-fold dosage increase to get the same shape of result as at when there was no 8-phenyltheophylline around. But in either case, what you see is a relationship that's very steep. Hill coefficients around 7. Oh. And yet we reinterpret that other one as being single site binding to the receptor with a Hill coefficient about 1. How does this happen? So that's the puzzler. Okay, if you have competition between binding sites, then you convert a normal single site binding process into a pseudo switch-like receptor kinetics. And this happens if branch point kinetics at enzymes or in any location where you have a set of competing processes. So competing with the A2 receptor for whatever adenosine it can grab are large sets of transporters of low affinity but high capacity sitting in the interstitium. Slides that curve over so you get this steep relationship with high Hill coefficients. So now let's compare those two sets of experiments. The first one we looked at was to block the kinase, and in that case you've got a surge of adenosine being released from cardiomyocyte, from endothelial cell, from smooth muscle cell, and impacting the receptor on the smooth muscle cell. So that looked like a first order binding process. Here we have this other situation. We've got an ADO adenosine infusion at various concentrations into the capillary flow, entering here, being taken up on the back side and the front side of the endothelial cell, being taken up through the transporters into the cardiomyocyte and reacted, drops quickly into the ATP pool inside the cardiomyocyte and the endothelial cell, taken up by the smooth muscle cell, all in competition to this poor leftover receptor. And so it gets this very high Hill coefficient simply because the geometric arrangement of these receptors, transporters competing with the receptor. This space is really small. It glows as small as 0.3 micron in the heart between the endothelial cell backside and the front side of the nearest side of the cardiomyocytes. So this is an interesting kind of geometric influence on that It would apply also when ATP is released in the cell. I put the alkaline phosphatase on here because the upstream end of the capillary is loaded with alkaline phosphatase. The downstream end of the capillary is loaded with dipeptidyl peptidase. This stains purple. The dipeptidyl peptidase stains red, so they're backwards. The capillaries should be red at the upstream end and blue at the downstream end, shouldn't they? Okay, so this was an example of saying we need to use the anatomy. Now I want to step aside and talk a little bit about going toward the genome. And I'm going to reveal my skepticism. But we're starting from the middle out, right? We start with what is known, we build on it. We need training. We use models as vehicles for our current thinking. Here's my belief. I express it in mathematical form. And now it's precise and it can be criticized. For multi-scale modeling, it gets more complicated, but it's the same idea. The idea of having a full multi-scale physiome with all of the ingredients from the transcription level through to the phenotype seems quite impossible for a long, long time into the future, probably forever, and not very practical. So that we probably need to have less rigidly structured models which can be revised by replacing modules for particular purposes. And part of the next stage of our work is on how to use multi-modular construction of detailed models and have that automated so that we can reconstruct models ad lib. And that's using this same kind of idea that we've talked about. So what about systems biology? As physiologists and mathematical analysts, we tend to look oddly at the systems biology community that has developed compartmental models, first order differential equation based models, and don't have much more in it. There's no place for anatomy in those kinds of models. The gene regulatory systems that people have worked so hard on with mRNA array analysis are hard to get at, hard to get precise information. Poor quantitation, lack of certainty in the linkages. Basically, now beginning to get kinetics, but it's really difficult. So I think we need to take pity on the poor systems biologist who's got this wealth of information that's hard to connect the ingredients. And it's a valiant struggle, and I believe that the easiest way for them to effect their results is to link it to the middle levels where we have a lot of knowledge, and the kinetics, and the coherence, and the cause and effect relationships. This is a protein interaction network, the interactome. And there are a lot of these being developed now. This one's about diabetic nephropathy in Pima Indians. Grind up the cells, use a variety of techniques to get the information on the relationships between these things. Yeast 2 hybrid's a good technique, but others, like how close are they to each other on the DNA? What's the heritage of these particular components? What are the time sequence of mRNA profile changes? That starts to get at cause and effect. But what's missing in here are regulatory features. And the one that disturbs me most of all is that the proteins that are interacting may have never seen each other prior to those reaction steps. They come from different mitochondrial, SR, et cetera, even from different cell types, and they're all mixed together. And by hydrophobic interactions, they're bound to interact, but it may not be a meaningful binding. So I look with a lot of skepticism on these constructed networks, and so do the people involved. As Trey Eidecker put it, he says, we've got 50 of these networks, literally in the community of PPI workers, and none have been validated. Part of the reason for that is that the validation is difficult, and the inclination of the computer science guys, which are so skilled at the analysis, is not to do experiments. Linking to the phenome. Diseases are experiments of nature. The Celestial Committee, that would be intelligent design, that would be evolution. Relatively few phenotypes are attributed to one gene. Cystic fibrosis is a good example. Huntington's would be another. But major diseases are multigenic. Phenotype, as Dennis has carefully explained to us, is determined by environment, accident, infection, nutrition, not just genetics. There's lots of switching going on that at crises in lives that change the transcription situation over time. Well, what about looking at phenotypic disease networks? And this was an idea that was looked at by Hidalgo and Laszlo Barabasi. They looked at actually 31 million people and age 65 to 95 in a database, and looked at the morbidity over about a 20-year period from these diseases, namely the identification that people had the disease. And the question is, what other diseases might they have that were related? So they classified all the diseases, and each point on here is a disease classification. And on one of their graphs, they had them different sizes for different occurrences of disease. They colored the class of disease. The line thicknesses between the nodes is a representation of the correlation in occurrence. All right, so they made raw calculations just on the numbers that have two diseases, any two, and that's what's mapped up here. In the lower one, they corrected these raw correlations for the frequency of the disease in the population as a whole. So these were the two calculations they used. The relative risk is the number of people with both diseases times the total number of patients N divided by the prevalence, the relative fraction of the whole population that had disease I and disease J. So that's the raw relative risk. This one is the same thing corrected for the population prevalence. The PDFs of these correlations, correlated diseases, are really very different waveform. So which one is better? It's hard to say. It's really on your point of view. You'd think that this one would be better. So let's look at that one. This is using the phi correlation on a particular subset of the map. And so what I did to analyze it, all their database is online, so you can do all of this by going to their database, and I think our slides are going to be up so that people can get them in retrospect. So I just took ones that looked like heavy-duty nodes with lots of thick lines connecting them, and asked, what are they? So I picked this set, and yeah, that looks like a reasonable set just to try out. And what are they? Oh, well, lo and behold, they don't appear to be. These would be related. This doesn't look particularly related. Airway obstructive. This was my central point. Pulmonary hypertension, dehydration, diaphragmatic hernia, and so difficult to say, oh, what's cause and effect here? Am I going to learn cause and effect relationships from these statistical associations? Not so evident. So I think this is going to have to be taken down to the physiological level in order to make the connection. You can see that some of these might be things that happen near death. You get urinary or bacterial infections. You certainly have malnutrition and dehydration. So these could be end-stage things. This is when I hit the button, it's supposed to quit here. Oh yeah. So, near death? Mm-hmm. So I think this idea is interesting, but not likely to yield. And so my conclusions are use integrative models, intact, in vivo, wherever what can be done. Comprehensive, accurate, realistic models. That's what this whole conference has been so strong in. Reverse engineering is what we're all after. These regulatory networks, proteomic and gene regulatory, are really difficult. They'll be elicitable through connection to what is known, biochemical networks, signaling networks, and so on. And finally, the phenotype. We'll get them to link up eventually, but again, by connecting with the middle. Nick, thank you very much. Thank all of the organizers. It's been a wonderful meeting from my point of view. I've enjoyed it absolutely thoroughly. The presentations have been really good, and I think the level of science here that's been exhibited is almost unparalleled. It's a very densely informative conference. So thank you all.
Okay, so while the next talk is setting up, any questions, burning questions?
So, Jim, it's a masterful presentation, thank you. As one at the genomics phenotype end of things, obviously I don't quite agree with you on some of the issues, but I had two questions. One is, when you infuse adenosine, as you did physiologically, into the heart circulation, but what about all the other things going on in the endothelial cell? Because presumably the high level of adenosine would inhibit ATP to AD2 adenosine degradation in the boundary layer of the endothelial cell, which goes on all the time. So you may actually have an ATP-ADP stimulation of nitric oxide release from the endothelial cell, which would influence your physiological readout, which was the flow change. So my point is that without the devil's in the details, and without a more comprehensive association and measurement of those details, then the interpretation, for example, your Hill plot, may in fact not be related to what you think it's related to. And so, I sort of do err down towards the detailed scales a little more than I think, which you're quite critical of. Would you care to comment on that?
Oh, Peter, you're right on. The example I gave was chosen to be simplified, and I gave you the hint that we're after the ATP release as well, because that gets immediately hydrolyzed through the alkaline phosphatase, et cetera, et cetera. So these are much more complicated than I could portray in this to make the point. And as you say, the devil is not only in the details, but that model then is a hypothesis which will soon be discarded in favor of a more complex one. So that's always going to happen. Every model is wrong.
That's a good point to stop.